Hello. Welcome to the course of Geography of Turkey 1, Physical Geography of Turkey. In this lesson, we will explore fundamental geomorphological features of Turkey. Please feel free to share your questions and insights through the eCampus platform or via email. Today, the crustal components that make up the landmass of Turkey have formed through a process that began before the Paleozoic era. These crystalline massifs, in the form of plutonic masses, constitute the foundation of the Neotethys Ocean, which reached its maximum extent during the Middle Jurassic to Middle Triassic period, 175 to 245 million years ago, either forming the basis of this sea or rising as islands above it. The end of the Upper Cretaceous, 66 million years ago, marks the period when contraction-closure movements began in the Neotethys Ocean. The movements, initially in the form of subduction zones on the ocean floor, generally manifested as an uplift-compaction in Northern Anatolia, Pontides, towards the end of the Cretaceous, Ketin 1966, 1983. This belt, consisting of the northern branch of Neotethys to the south, crossed the ophiolitic and limestone nappe slices of Anatolia, Anatolians, in Central Anatolia, Menderes and Kırşehir massifs, pushing onto the settled autochthonous series of the Taurus Mountains, Toros. Following these significant changes at the end of the Cretaceous, Anatolia's four main tectonic belts, namely the Pontides, Anatolides, Taurides, and Southeast Anatolia, began to take shape with their distinctive features. In the ancient Tertiary period, 66 to 2.6 million years ago, even if Neotethys did not retreat from the Turkish territory, it acquired a feature of filling the troughs and basins between the newly emerging mountain ranges. Therefore, the Old Tertiary period is the era when the initial forms of basins, which would later generally transform into plains, appeared especially in the Pontide and Anatolide belts, where the mountainous framework had previously formed and developed in Anatolia. The younger Taurides, along with the basins in eastern and southeast Anatolia, were added to this system as they completed their development during the Neogene, 23 to 2.6 million years ago. Middle Upper Cretaceous, 100.5 million years ago, 66 million years ago, and Paleocene, 66 million years ago, 56 million years ago, Middle Upper Cretaceous and Paleocene. During this period, the appearance of Anatolia is not very different from the Jurassic Lower Cretaceous. However, towards the end of the Upper Cretaceous, compression began, and with the Laramide movements between the Upper Cretaceous and Paleocene, the closure of the Rhodo-Pontide Arc in the south and the opening of the Black Sea in the north began. In the Pontides south of the Black Sea, including the Sakarya continent, compression, thrusting, and the formation of a melange on the southern edge of the thrusting occurred. In the eastern Pontides, granite intrusions occurred. This event is a result of the northward subduction of the northern branch of Neotethys. On the southern edge of the same ocean, the ocean floor material, ophiolites, limestones, etc., forming the Elmul-Bozkır, Lycia, nappes began to override the northern edge of the Anatolian Tauride platform further south. At the same time, thrusts towards the south began to occur south of the Anatolian Tauride platform. Meanwhile, Cyprus shifted southward, the Alanya Massif, and its extensions separated from the Anatolian Tauride platform. In the east, thrusts were also observed on the Arabian platform. In contrast, there were local northward thrusts on the northern edge of the Bitlis Massif, for example. However, generally speaking, the Bitlis, Kırşehir, and Menderes massifs were buried beneath the thrusting masses coming from the north and underwent intense metamorphism. Paleocene-Eocene. During the Paleocene-Eocene period, the closure of the Neotethys branches, which had started compressing earlier, was generally completed, Brinkman 1976, Sadam. Due to the Laramide movements at the end of the Cretaceous, erosion surfaces formed on the ancient continental fragments rising between the troughs. Many extensive sections of those on the Pontides have continued to erode since then and have completely lost their original form today. Surfaces found on some massifs in the Taurus Mountains, covered by younger formations, have turned into fossil, DF systems, erosion surfaces. The formation of bauxite is considered evidence of the brief emergence of Upper Cretaceous formations to the water's surface. The Cenozoic. The tectonic movements at the end of the Upper Cretaceous, Laramide, played a crucial role in shaping the current morphology of Anatolia. Consequently, east-west oriented mountain ranges and intermountain basins were formed during the Cenozoic era, particularly in the troughs. Continuous sedimentation occurred throughout the Cenozoic, serving as correlated deposits for the erosion in the rising mountainous regions, Ketin 1983. In the early Tertiary, the remnants of the Cretaceous seas or the seas resulting from the Eocene transgression filled the troughs in the Pontide and Anatolian belts, predominantly becoming the places where lacustrine continental sediments accumulated during the young Tertiary. In the late Tertiary, marine sediments, which entered the Marmara and Bosporus, and marine sediments filling the southern slopes of the Taurus Mountains and the troughs of southeast Anatolia, were formed. This marine sedimentation came to an end in the South Taurus Mountains and southeast Anatolia in the Upper Pliocene, and Anatolia became entirely terrestrial during the Quaternary. According to Ketin, 1983, the Cenozoic basins where continuous sedimentation occurred include Thrace, Bigade, Soma, Ushak, Kelkit Valley, Haimana, Tuzgalu, Yozgat, Sungarlu, Ulyaxla, Shivas Zara, Darend Balaban, Muz Hns, Adana, and southeast Anatolia. Some of these basins completed their formation at the end of the Neogene. Therefore, these basin groups are referred to as tertiary basins. Another group of basins began forming in the early Neogene and continued their formation mostly during the Quaternary. These basin groups are also called Neogene basins. In other words, there are basins that continued their formation during the Paleotectonic period until the early Tertiary Middle Miocene. In contrast, there are basins that have started or completed formation during the Neotectonic period. However, except for the Sungas Basin in southeast Anatolia, the common feature of almost all of them is that the formation of ophiolitic formations, symbolizing the thickening of oceanic crust, ended at the beginning of the Cenozoic. Subsequently, Fleisch, molasse-type sediments, and later lacustrine and continental fluvial deposits filled these basins. All these recent accumulations are sediments correlated with the ongoing erosion in mountainous areas. Brinkman, 1976. Paleogene. During the Paleocene-Eocene period, a transgressive marine environment prevailed over Anatolia, particularly from Paleocene to Middle Eocene, except in the Pontide ranges and the more southern Anatolian sections where the land had already undergone terrestrialization. Brinkman 1976, Ketin 1983. The prominent basins existing in the Paleogene include Thrace, Kelkit Valley, Haimana Tuscalu, Sungarlu, Ulyaxla, Shivas Darend, Muz Hns, Ketin 1983. Among these basins, marine sedimentation, which started in the Middle Eocene in Thrace, ended in the Mid-Oligocene. Brinkman 1976. In Zonguldak, Giresun, Bilegic, Shivas, and western Toros, marine sedimentation ceased at the end of the Eocene. Although the marine regime entirely came to an end in southeast Anatolia, the Oligocene still represents a regressive period. This event occurred as a result of the Pyrenean, Helvetian, and Savian tectonic movements during the beginning, middle, and end of the Oligocene. In the paleotectonic map of the Eocene, Ketin 1983, Senger and Yilmaz 1983, the northern parts of the Pontides, Anatolides, and Toros ranges are undergoing terrestrialization. In other words, the Anatolian plate is beginning to form. Particularly in the Toros belt, there are southward thrusts in the form of slices, and there are observations of the southern parts of Toros, which constitute land masses such as Gyrate and Cyprus, remaining further south. However, in the Antalya and Sukurova basins, a setback in basin formation are observed. Despite the terrestrialization of central and western parts of Anatolia, it is observed that the eastern Mediterranean waters filled the Kaban, Maidan, and Sungas basins in southeast Anatolia, and the Munjir and Malatya Bitlis massifs rose as narrow islands above this sea. In Munjir, Cyprus, and south of Crete, there is a distinct subduction and abduction line. This period marks the second active phase of the Elmul-Bozkır, Lycian, nappes in western Toros. The erosion surfaces belonging to the Upper Eocene-Oligocene phase, during which large parts of Anatolia underwent terrestrialization, are largely observed today as fossil surfaces. According to the Aral system, they are observed as DF surfaces. However, in the highest parts of some mountain masses, although significantly damaged, possible Oligocene erosion surfaces can be observed in the Aral system as D0 surfaces. This erosion, which began in the Oligocene in the mountainous areas of the Pontide and Anatolian belts, continued throughout the Neotectonic periods, i.e., Neogene and Quaternary, filling the basins with correlated lacustrine continental, fluvial, formations. The erosion and accumulation surfaces, aged according to these correlated sediments, were defined and explained by Aral as D0, DI, D2, D3, D4 systems. Paleogene. During the Paleocene-Eocene period, a transgressive marine environment prevailed over Anatolia, particularly from Paleocene to Middle Eocene, except in the Pontide ranges and the more southern Anatolian sections where the land had already undergone terrestrialization. Brinkman 1976, Ketin 1983. The prominent basins existing in the Paleogene include Thrace, Kelkit Valley, Haimana Tuscalu, Sungarlu, Ulyaxla, Shivas Darend, Muz Hns, Ketin 1983. Among these basins, marine sedimentation, which started in the Middle Eocene in Thrace, ended in the Mid-Oligocene. Brinkman 1976. In Zonguldak, Giresun, Bilecik, Sivas, and western Toros, marine sedimentation ceased at the end of the Eocene. Although the marine regime entirely came to an end in southeast Anatolia, the Oligocene still represents a regressive period. This event occurred as a result of the Pyrenean, Helvetian, and Savian tectonic movements during the beginning, middle, and end of the Oligocene. In the paleotectonic map of the Eocene, Ketin 1983, Senger and Yilmaz 1983, the northern parts of the Pontides, Anatolides, and Toros ranges are undergoing terrestrialization. In other words, the Anatolian plate is beginning to form. Particularly in the Taurus belt, there are southward thrusts in the form of slices, and there are observations of the southern parts of Toros, which constitute land masses such as Gyrate and Cyprus, remaining further south. However, in the Antalya and Sukurova basins, a setback in basin formation are observed. Despite the terrestrialization of central and western parts of Anatolia, it is observed that the eastern Mediterranean waters filled the Kaban, Maidan, and Sungus basins in southeast Anatolia, and the Munjir and Malatya Bitlis massifs rose as narrow islands above this sea. In Munjir, Cyprus, and south of Crete, there is a distinct subduction and abduction line. This period marks the second active phase of the Elmul-Bozkır, Lycian, nappes in western Toros. The erosion surfaces belonging to the Upper Eocene-Oligocene phase, during which large parts of Anatolia underwent terrestrialization, are largely observed today as fossil surfaces. According to the Aral system, they are observed as DF surfaces. However, in the highest parts of some mountain masses, although significantly damaged, possible Oligocene erosion surfaces can be observed in the Aral system as D0 surfaces. This erosion, which began in the Oligocene in the mountainous areas of the Pontide and Anatolian belts, continued throughout the neotectonic periods, i.e., Neogene and Quaternary, filling the basins with correlated lacustrine continental, fluvial, formations. The erosion and accumulation surfaces, aged according to these correlated sediments, were defined and explained by Aral as D0, DI, D2, D3, D4 systems. Neotectonic periods. 6.1. Neogene Quaternary DS systems. The Paleotectonic period of Anatolia, which had undergone terrestrialization during the Oligocene movements, meaning the formation of formations constituting Anatolia in the sea, ended in the Neogene. The Paratethys, an inland sea north of the Alpine mountain range, was formed, and to the south, it transformed into the Tethys Mediterranean. The terrestrial formation and development of Anatolia, as well as its geomorphological evolution, occurred during this period. In this period, Anatolia took its final shape through folding, faulting, and erosion, and Neogene and Quaternary stages, which cannot be distinctly separated according to geological data, were clearly distinguished using geomorphological methods, i.e., through the use of marine formations with lateral transitional terrestrial formations and erosion surfaces. Therefore, the Neogene and Quaternary geomorphological stages opened here are more detailed than the geological stages. These stages are in the form of 5 main periods. The first 4 of them are numbered from old to new with the D symbol, but the 5th period covering the younger part of the Quaternary is defined as S systems since it can be more detailedly distinguished with landforms, terraces. These systems are shown in Table 1. Regarding stratigraphy in this table, the point to be noted is the event of placing the Pontian and Pannonian, belonging to the Paratethys and penetrated into the lower Pliocene before 1980, see, for example, Brinkman 1976, into the Upper Miocene after 1980, and accepting them as equivalents to the Tortonian and Messenian in the Tethys stratigraphy. Therefore, age determinations in publications before 1980 would be misleading if evaluated without considering this point. This issue can be easily and accurately resolved by taking into account the erosion accumulation surfaces in the Aral system and their correlated layers. According to this schematic representation, erosion surfaces in the mountains are observed in successive steps, while accumulation surfaces have developed in the basins. In basins where sedimentation is continuous, accumulation surfaces have turned into fossil surfaces since older sediments have been covered by younger ones, and the youngest surfaces have remained observable. However, in basins where subsidence events continued in the middle, if young sediments only filled the central part, accumulation surfaces can be observed as progressively younger steps from the edges. Transition areas between mountains and basins show a more variable characteristic. Here, due to uplifts at the mountain edges, accumulation, sedimentation, surfaces have not been covered, and erosion, denudation, surfaces are observed in an exposed, exhumed, state. Sometimes, it is observed that erosion surfaces in the mountains continue as accumulation surfaces on the correlated sediments in the basins. In that case, the term erosion accumulation surface is used. In these stages, for whatever reason, when erosion became active, undulating or even steep relief was formed. Where erosion weakened, especially towards the end of the period, gently sloping or nearly flat surfaces were formed. Therefore, the periods marked with symbols started immediately after the closure of the previous period, underwent a certain evolution, and after that, acquired the final form observed today. For example, the Upper Miocene period, indicated by the symbol D2, began with tectonic movements in the Tortonian beginnings, continued with the development of channel-shaped depressions or Piedmont plains under humid tropical conditions, sometimes reaching a width of 10 kilometers and a depth of several hundred meters. It progressed with the semi-arid warm climatic conditions in the Messinian, acquiring the characteristics of a shape ensemble consisting of extensive pediments, terrestrial deposits with mammal fossils at their base, even gypsum playa deposits, rocky ramps at the upper edge of the pediments, and conical rocky adodypals. Mountain formation. Mountain formation refers to the geological processes that underlie the formation of mountains. These processes are associated with large-scale movements of the Earth's crust, tectonic plates. 1. Folding, faulting, volcanic activity, igneous intrusion and metamorphism can all be parts of the orogenic process of mountain building. The formation of mountains is not necessarily related to the geological structures found on it. The understanding of specific landscape features in terms of the underlying tectonic processes is called tectonic geomorphology, and the study of geologically young or ongoing processes is called neotectonics. From the late 18th century until its replacement by plate tectonics in the 1960s, geosyncline theory was used to explain much mountain building. There are 5 main types of mountains: volcanic, fold, plateau, fault block and dome. A more detailed classification useful on a local scale predates plate tectonics and adds to these categories. The formation of volcanic mountains is closely tied to the processes associated with volcanic activity, which involves the eruption of magma, ash, and gases from beneath the Earth's crust onto its surface. The creation of volcanic mountains often occurs at plate boundaries, where tectonic plates interact. In the context of Turkey, there are several volcanic regions with notable volcanic mountains. Here are some key areas. 1. Anatolian Peninsula. The Central Anatolian volcanic province is a significant volcanic region in Turkey. It includes the Irshais, Hasan, and Menderes mountains. These volcanic structures were formed through both explosive and effusive volcanic activities. 2. Eastern Anatolia. Mount Ararat, Agirdag, is Turkey's highest peak and a dormant volcanic mountain. It is a stratovolcano that has experienced both effusive and explosive volcanic activities in its history. 3. Aegean region. The Greek island of Santorini, though not part of Turkey, is geologically related to the region. Santorini's volcanic activity has played a role in the geological history of the eastern Mediterranean. 4. Northwestern Turkey. The region around the Sea of Marmara, including the Biga Peninsula, has experienced volcanic activity. Mount Ida, Kazdag, in the Biga Peninsula is an example of a volcanic mountain. The formation of these volcanic mountains is associated with the tectonic complexity of the region. The Anatolian plate is situated between the Eurasian plate to the north and the African plate to the south. The interactions and movements of these plates have led to the creation of various geological features, including volcanic structures. The volcanic activity in Turkey has contributed to the diverse landscape of the country, providing fertile soils and influencing regional ecosystems. While some of these volcanic mountains are currently dormant, the potential for future volcanic activity remains, and monitoring is essential for understanding and mitigating potential hazards. Fold mountains are formed through the tectonic processes of plate collision and the subsequent folding of rock layers. These mountains typically have long, linear ridges and valleys, and their formation is associated with convergent plate boundaries. Turkey is situated in a tectonically active region, and several fold mountain ranges have been shaped by complex geological processes. Here are some key aspects of the formation of fold mountains and examples from Turkey. Formation of fold mountains. 1. Plate collision. The primary mechanism for the formation of fold mountains is the collision of tectonic plates. When two plates converge, one plate may be forced over the other in a process known as subduction. As the plates collide, intense pressure leads to the deformation and folding of the Earth's crust. 2. Folded rock layers. Sedimentary rock layers, originally horizontal, undergo deformation and folding due to compressional forces. Anticlines and synclines are common structural features in fold mountains. Anticlines are upward folded arches, while synclines are downward folded troughs. 3. Uplift and erosion. The folded rock layers are uplifted to form mountain ranges. Erosion, caused by various agents such as water, wind, and ice, exposes the folded structures. Over time, the mountains continue to rise and erode simultaneously. Fold mountains in Turkey. 1. Taurus Mountains. The Taurus Mountains, Toros Dağlar, in southern Turkey are a significant fold mountain range. They run parallel to the southern coast of Turkey and are characterized by complex geological structures formed through the collision of the African and Eurasian plates. 2. Pontic Mountains. The Pontic Mountains, Kuzey Anadolu Dağlar, extend along the northern coast of Turkey, running parallel to the Black Sea. They are a result of the collision between the Eurasian and Anatolian plates. 3. Anti-Taurus Mountains. The Anti-Taurus Mountains, Aladağlar, located to the north of the Taurus Mountains, are another example of fold mountains in Turkey. They are associated with the collision and convergence of tectonic plates. 4. Bitlis-Zagros Suture Zone. The Bitlis-Zagros Suture Zone in eastern Turkey represents the tectonic suture between the Anatolian plate and the Iranian plate. It has played a role in the formation of mountainous terrain. Turkey's diverse topography, influenced by tectonic activity, has created a landscape with a mix of fold mountains, volcanic peaks, and other geological features. The ongoing tectonic processes contribute to the dynamic nature of the region. Block mountains, also known as horst and graben structures, are formed by the extension or stretching of the Earth's crust, leading to the creation of elevated blocks, horsts, and down-dropped blocks, grabens. This type of mountain formation is associated with divergent tectonic plate boundaries and the process of rifting. Here's an overview of the formation of block mountains and examples from Turkey. Formation of block mountains. 1. Rifting. Block mountains form in regions where the Earth's crust is undergoing extension. This extensional tectonic activity leads to the formation of rift zones, where the crust is pulled apart. 2. Horst and graben structures. As the crust extends, it creates alternating blocks of elevated terrain, horsts, and lowered areas, grabens. The horsts remain uplifted, while the grabens subside. The blocks are bounded by fault lines. 3. Faulting. Normal faults are common in regions undergoing extension. These faults allow the crust to stretch and move downward along the fault lines, creating the characteristic block structures. 4. Uplift and erosion. The elevated blocks, horsts, eventually become block mountains. Over time, uplift continues, and erosion exposes the geological structures of the mountains. Block mountains in Turkey. 1. Armenian Highland, Anatolian Plateau. The Armenian Highland, which includes the Anatolian Plateau, is an example of a region where block mountain processes have contributed to the topography. The Anatolian Plateau is characterized by uplifted blocks, faulting, and extensive volcanic activity. 2. Sancur Basin and Kırşehir Block. The Sancur Basin and Kırşehir Block, located in central Turkey, represent a region where block faulting has occurred. The basin is a graben structure, and the surrounding blocks have been uplifted. 3. Denizli Basin. The Denizli Basin, situated in western Turkey, is another example of a region with block faulting. The basin is a graben structure, and the surrounding blocks have undergone uplift. 4. Çatalca-Kocaeli Block. The Çatalca-Kocaeli Block, located in the vicinity of Istanbul, is associated with the North Anatolian Fault. This region has experienced significant tectonic activity, leading to block movements. The tectonic complexity of Turkey, influenced by the interaction of several major plates, has resulted in diverse mountain formations, including block mountains. The geological history of the region is marked by the interplay of extensional and compressional forces, shaping Turkey's varied landscape. Uplifted passive margins are geological formations characterized by the emergence of continental margins that were once passive, non-tectonically active regions. These margins experience uplift due to various geological processes, often associated with tectonic activity and crustal dynamics. While Turkey is not commonly associated with uplifted passive margins, the region has undergone complex tectonic interactions, and some areas exhibit characteristics that may align with uplifted passive margin features. Formation of uplifted passive margins. 1. Initial passive margin. The region begins as a passive margin, characterized by a lack of significant tectonic activity. Passive margins often form along continental shelves adjacent to oceanic crust. 2. Tectonic activity. Tectonic forces, such as the collision of tectonic plates, can lead to the reactivation of formerly passive margins. This reactivation may result from subduction, continental collision, or other geological processes. 3. Uplift and erosion. Uplift occurs as a response to tectonic forces, causing the passive margin to rise. Concurrently, erosion processes shape the landscape, exposing geological structures. Examples of uplifted passive margins in Turkey. While Turkey is more commonly associated with active tectonics, several regions have experienced complex geological histories that may include aspects of uplifted passive margins. 1. Taurus Mountains. The Taurus Mountains in southern Turkey have been shaped by the convergence of the African and Eurasian plates. While not a classic example of an uplifted passive margin, the Taurus Mountains have been influenced by the tectonic interactions between these plates, leading to uplift and mountain building processes. 2. Central Anatolian Plateau. The Central Anatolian Plateau is a region with complex geological features. While it has been influenced by both extensional and compressional tectonic forces, some areas may exhibit characteristics of uplifted passive margins as a response to regional tectonics. 3. Western Anatolia. Western Anatolia, including areas around Izmir, has experienced tectonic activity related to the North Anatolian Fault. This region's geological history involves the interplay of extensional and compressional forces, potentially leading to uplifted features. It's important to note that Turkey's geological evolution is primarily associated with active tectonics, including the convergence of major plates. While uplifted passive margins may not be the dominant geological feature, the region's complex tectonic history has contributed to diverse landscapes and geological formations. Formation of plateaus. Plateaus are elevated flatlands or gently rolling areas characterized by relatively flat terrain at a higher elevation than the surrounding landscape. The formation of plateaus involves geological processes that lead to uplift, erosion, and the development of a flat or gently undulating surface. Here's a general overview of the formation of plateaus. 1. Uplift. The initial stage often involves tectonic uplift due to the collision of tectonic plates or other geological forces. This uplift raises a portion of the Earth's crust to higher elevations. 2. Erosion. Once uplifted, plateaus are subject to erosional forces such as rivers, wind, and glaciers. These processes gradually wear down the elevated areas, exposing flat or gently sloping surfaces. 3. Stratification. The geological composition of plateaus can include layered sedimentary rocks, volcanic deposits, or other resistant materials that contribute to the plateau's characteristic flatness. 4. Volcanic activity. In some cases, plateaus form through volcanic activity where extensive lava flows cover large areas. Over time, these lava plateaus can undergo erosion and contribute to the formation of flat surfaces. 5. Tectonic processes. Plateaus may result from tectonic processes such as continental rifting, where the Earth's crust is stretched, creating elevated plateaus between the separating plates. Examples of plateaus in Turkey. 1. Anatolian Plateau. The Anatolian Plateau is a vast elevated region in Turkey that has undergone complex tectonic processes. It is characterized by flat to gently rolling terrain and has been shaped by the interaction of the Anatolian and Arabian plates. 2. Eastern Anatolian Plateau. The Eastern Anatolian Plateau is another significant plateau in Turkey, bordered by mountain ranges. It has been influenced by tectonic activity related to the convergence of the Anatolian and Eurasian plates. 3. Central Anatolian Plateau. The Central Anatolian Plateau, situated between the Pontic and Taurus mountain ranges, is known for its relatively flat landscape. It has been shaped by tectonic forces and erosion over geological time. 4. Malatya Plateau. The Malatya Plateau, located in eastern Turkey, is an example of a smaller plateau region within the broader Anatolian context. It reflects the geological processes that have shaped the plateau landscapes in the region. While these plateaus may not fit the textbook definition of perfectly flat surfaces, they exhibit characteristics of elevated and relatively flat terrain resulting from geological processes such as tectonic uplift and erosion. The specific geological history of each plateau in Turkey contributes to its unique features. Formation of plains. Plains are extensive, relatively flat areas of land that often have minimal elevation changes. They are formed through various geological and environmental processes. Here are the key factors contributing to the formation of plains. 1. Depositional processes. Plains often develop in areas where sediments accumulate over time. Rivers, streams, and glaciers carry sediments like sand, silt, and clay from elevated regions and deposit them on lower lying areas. Over extended periods, these deposited sediments create flat or gently undulating plains. 2. Fluvial deposition. Rivers play a significant role in plain formation through the deposition of sediments. When rivers slow down as they reach lower elevations, they deposit sediment along their banks and floodplains. This process creates alluvial plains, which are common types of plains. 3. Glacial processes. Glaciers can shape plains through the deposition of glacial till and sediments. As glaciers move, they transport and deposit materials, contributing to the formation of plains. In areas where glaciers have receded, glacial outwash plains may emerge. 4. Aeolian processes. Wind-driven processes, known as aeolian processes, can lead to the formation of plains. Wind carries and deposits fine particles like sand, creating expansive sandy plains such as desert plains. Loess plains, characterized by wind-deposited fertile silt, are another example. 5. Tectonic subsidence. Some plains form due to tectonic subsidence, where the Earth's crust sinks, creating low-lying areas. Subsidence can occur along fault lines or in regions with extensional tectonics. Rift valleys, which are elongated plains, may form through this process. 6. Marine deposition. Coastal plains are formed through the deposition of marine sediments along coastlines. These plains may result from the accumulation of materials carried by rivers or from the gradual retreat of the sea, leaving behind sedimentary deposits. 7. Lacustrine deposition. Plains near lakes, known as lacustrine plains, are formed through the deposition of sediments in lake basins. Over time, as lakes accumulate sediment, flat plains may develop around the lake edges. 8. Human activities. Human activities, such as agriculture and urbanization, can contribute to the development of plains. The leveling of land for farming or construction can create artificial plains. Plains exhibit diverse characteristics depending on the geological and environmental processes that contribute to their formation, making them essential features of the Earth's landscape. Depositional processes contributing to plains in Turkey. Turkey, with its diverse topography and geological history, features several plains formed through various depositional processes. Here are some notable examples of plains in Turkey and the processes involved in their formation. 1. Çukurova, Cilician, Plain. Process, fluvial deposition. Description: Çukurova Plain, located in southern Turkey, is formed by the deposition of sediments brought by the Seyhan and Ceyhan rivers. These rivers transport alluvial materials from the Taurus Mountains to the Mediterranean Sea, creating a fertile and flat plain. 2. Konya Plain. Process, fluvial and lacustrine deposition. Description: the Konya Plain, situated in central Turkey, is characterized by a combination of fluvial and lacustrine deposition. The plain has been shaped by the interaction of rivers, including the Sultan Marshes, which is a remnant of a larger ancient lake. The accumulation of sediments from these sources contributes to the flatness of the plain. 3. Sarsamba Plain. Process, marine and fluvial deposition. Description: Sarsamba Plain, located along the Black Sea coast, is influenced by both marine and fluvial processes. The Samsun River and other smaller rivers transport sediments from the Pontic Mountains to the Black Sea. The accumulation of these sediments, combined with marine processes, contributes to the formation of this coastal plain. 4. Edirne Plain. Process, fluvial and aeolian deposition. Description: Edirne Plain, in the Thrace region, has been shaped by the Maritsa River and its tributaries. The river deposits alluvial sediments in the plain. Additionally, aeolian processes, driven by wind, contribute to the deposition of fine particles in certain areas. 5. Gediz Delta. Process, fluvial and deltaic deposition. Description: the Gediz Delta, located along the Aegean coast, is formed by the Gediz River. This river transports sediments from the interior to the Aegean Sea, leading to the formation of a deltaic plain. The interplay of fluvial and marine processes shapes the landscape. 6. Marmara Ireglisi Plain. Process, marine and fluvial deposition. Description: situated along the Sea of Marmara, Marmara Ireglisi Plain is influenced by marine and fluvial processes. Sediments transported by rivers and marine deposition contribute to the formation of this coastal plain. 7. Sorum plain. Process: fluvial and lacustrine deposition. Description: Sorum plain, located in Central Anatolia, is shaped by fluvial processes, particularly the Kırşehir River. Additionally, remnants of ancient lakes in the region contribute to lacustrine deposition, influencing the plain's characteristics. Fluvial deposition plays a significant role in the formation of plains in Turkey, contributing to the creation of fertile and flat landscapes. Here are some examples of plains in Turkey where fluvial deposition has been a dominant geological process. 1. Çukurova, Cilician, Plain. Location: Southern Turkey. Description: formed by the Seyhan and Ceyhan rivers, which carry alluvial sediments from the Taurus Mountains to the Mediterranean Sea. The deposited sediments create a fertile plain known for agriculture. 2. Konya Plain. Location: Central Turkey. Description: shaped by fluvial processes, particularly the Sultan Marshes, which is a remnant of a larger ancient lake. The rivers in the region contribute to the accumulation of sediments, forming a flat plain. 3. Gediz Delta. Location: Aegean coast. Description: the Gediz River transports sediments from the interior to the Aegean Sea, forming a deltaic plain. Fluvial processes are crucial in shaping the landscape and contributing to the fertile soils of the plain. 4. Sorum Plain. Location: Central Anatolia. Description: influenced by the Kırşehir River, which carries alluvial sediments to the plain. The river's fluvial activity contributes to the formation of a flat landscape suitable for agriculture. 5. Edirne Plain. Location: Thrace region. Description: shaped by the Maritsa River and its tributaries, with fluvial processes depositing sediments. Aeolian processes, driven by wind, also contribute to the deposition of fine particles in certain areas. 6. Bafra Plain. Location: Black Sea coast. Description: the Yeşilırmak River influences the formation of the Bafra Plain through fluvial processes, depositing sediments along the Black Sea coast. 7. Safe Lake Basin. Location: Central Anatolia. Description: the basin is characterized by fluvial processes from rivers such as the Kırşehir and Delice rivers. Sedimentation contributes to the creation of flat plains in the region. Fluvial deposition in these areas has not only shaped the topography but has also played a crucial role in the development of fertile soils, making these plains important for agricultural activities in Turkey. Tectonic subsidence plains in Turkey are formed due to the downward movement of the Earth's crust, often associated with tectonic activity. Here are some examples of tectonic subsidence plains in Turkey. 1. Aydın Basin. Location: Western Anatolia. Description: the Aydın Basin is a tectonic subsidence plain formed by the extensional tectonics along the Büyük Menderes Graben. The basin is characterized by horst and graben structures, with the Büyük Menderes River flowing through it. 2. Neogean basins of Western Anatolia. Location: various locations in Western Anatolia. Description: several basins in Western Anatolia, such as the Izmir, Gediz, and Baklan basins, are the result of tectonic subsidence during the Neogen period. These basins exhibit features of extensional tectonics. 3. Kütahya Dinar Basin. Location: Western Anatolia. Description: the Kütahya Dinar Basin is an extensional tectonic basin formed by subsidence along fault lines. It is surrounded by mountain ranges, and tectonic activity has influenced its geological evolution. 4. Çanakkale, Dardanelles, Basin. Location: northwestern Turkey. Description: the Çanakkale Basin, including the Dardanelles region, is influenced by tectonic subsidence associated with the North Anatolian Fault. The basin exhibits features of a pull-apart basin. 5. Manyas-Gönen Basin. Location: northwestern Anatolia. Description: this basin is formed by tectonic subsidence along the Saray Fault system. The Manyas-Gönen Basin is known for its lake and wetland environments. 6. Gaziantep Basin. Location: southeastern Anatolia. Description: the Gaziantep Basin is a tectonic subsidence plain formed by the interaction of the East Anatolian Fault and the East Anatolian Extensional Zone. It is part of the larger East Anatolian basin system. Tectonic subsidence plains are characterized by the sinking of the Earth's crust, creating low-lying areas often filled with sedimentary deposits. These plains can be influenced by various tectonic forces, including extensional or strike-slip movements.